Welcome back to the continuation of our chapter lasers. In the previous session, we had discussed the Einstein's coefficients. So that is A21 by B21 is equal to 8 by h nu cube by c cube, and B12 by B21 is equal to 1. Right? So now, in continuation to the Einstein coefficients, now we will be discussing an important topic in the exam point of view and also in the content and concept point of view in the lasers chapter. That is the most important topic called as a characteristics of lasers. So there are mainly 4 characteristics for the laser. These characteristics made the concept of laser very important and made the application in the point of technology. So now, what are the important characteristics? There are 4 characteristics, and these are inherent properties, or are inherent characteristics. And the first point is very important. That is called as a coherence. And the second characteristic is known as monochromaticity. And the third one is directionality. And the fourth one is intensity, or also called as a high brightness. So these 4 characteristics, these main important characteristics, made the laser most applicable in the engineering and technology. So for any laser, any applicative laser, either we are using the laser in the medicine, we are using in the laser in the mechanics, or we are using in the laser in biomedical engineering, and any field, these 4 characteristics makes the laser different from the ordinary light. So we will discuss in detail one by one. We will take coherence and we will discuss some important points. And once again, we will be discussing the monochromaticity, and we will be discussing some important points, similarly directionality and intensity. And before getting into the actual topic, these 4 characteristics are interrelated. They are related like a web, like a spider web, where this monochromacity is due to the coherence, and these 2 parameters decide the directionality, and these 3 parameters decide the intensity. So this is the order. In some textbooks the order will be shuffling, but in the present context and in the present topic we will discuss the order like this only, because the coherence leads to monochromacity, and this monochromaticity and coherence leads to directionality, and these 3 parameters decides the intensity. So let me go for the first introduction, or the first topic of coherence. Right? Then what is the coherence? Right? So if I split the word coherence, there is an uttering of the sound called as a herence. Herence means it is a property by which it possesses inherent property, and that property will be a common point. Hence the word coherence. Right. This is a phenomena, or this is a phenomenon exhibited by the light or the radiation. Right. What is the coherence? The coherence is the predictability correlation. So I'll try to write the keywords such that you can make a note. So it is the predictability correlation between the phase and amplitude. So these phase and amplitude are important properties for any radiation, any light radiation. For example, you know the basic term phase, which represents the state and position of a wave, and the amplitude is nothing but the height of the simply we can say this is the height of the wave, or it is the distance from mean position to extreme position if we represent the light in the form of a wave. And you know that the phase is the position or a point where it is in the mean position or an extreme position, or left extreme or right extreme. So these it is the predictability between the phase and the amplitude are at one point in a wave with I am just correlating I am calculating the phase and the amplitude at one point in a wave, and I am correlating that phase and amplitude with another point, in the same wave, or either it may be a neighboring wave, or either it may be another wave, okay, or adjacent wave. Right. This is the definition, basic definition, which is very important. So if you are very clear of what is the correlation and how we are correlating at different points, then the coherence topic will be very easy. Right? It is a predictability. It is the assumption or the nearness of assumption or the nearness of a hypothesis where we are correlating the phase and the amplitude at one point in a wave and just comparing or correlating with the same phase and amplitude at another point in the same wave. Or we can, I will extend the definition, at one point in the wave with the phase and the amplitude at another point in the same wave. Right. Let me go for a diagram, then it will be very clear for you. For example, let us consider, so this is a wave. Right. Now, I will calculate, so this is the direction of propagation, right? And I will calculate at a point, say this is the point P1, where this is the phase, and I will calculate the amplitude. Now, I can correlate the point at this point where I am calculating the phase and the amplitude with another point. Let us consider, so this is the point 2. So this is how I am comparing that P1 and P2. P1 and P2 are the points where I had calculated the phase and amplitude. Here also at point P2 I have calculated the phase and amplitude. Now if I correlate that P1 and P2 are a little bit similar, or they are almost nearness which I am predicting. So it may happen. That is called as a prediction and the correlation. Then this phenomena is said to be coherence, where you see that the particles of the vibration are in same phase throughout the wave. So this is one aspect. Then coming to the second point, are neighboring wave. So let us consider another wave. So say this is the first wave like this, and say this is another neighboring wave which is propagating. Now if I say, so this is a point P1, I am calculating the phase and amplitude at point P1 in one wave, and I am also calculating the same phase and amplitude in the another wave. Now if I correlate this P1 in the one wave and P2, that is wave and amplitude of the neighboring wave, then these 2 points are in coherence. That means the 2 waves or the particle vibrations are in the coherence. Right? So now the coherence is of 2 types. Coherence is of 2 types. The first type is temporal coherence. And the second type is temporal coherence, or there is another name called as a longitudinal coherence. And another type is spatial coherence, or also called as a transverse coherence. Right? So these are the 2 parts of the coherence. Coherence is of 2 types, a temporal coherence and a spatial coherence. Let me go for what is a temporal coherence. Right? So the temporal coherence, if I go for the discussion and the clarification with the divisions side by side, how the 2 names are bifurcated. Right? So first we will be discussing what is a temporal coherence. Temporal coherence, and at the parallel we will be discussing a spatial coherence. Right? So this temporal coherence and spatial coherence are the 2 cases of a 2 types or 2 cases of a coherence. There is a name itself, a temporal coherence. The temporal coherence, it is a possible it is possible to predict the correlation of the important words same phase and amplitude at one point in the wave with respect to the phase and amplitude with the same phase and amplitude at another point of the same wave. This is more important, of the same wave. So let me go for the diagram. For example, a wave is propagating like this. So this is the wave propagating, and now if I consider, say, this is a point P1, and say I am calculating here the phase and amplitude, and I will call it as a point 2, where I will calculate phase and amplitude. Now I will say that P1 and P2 are the amplitude and the phase at one point and another point of the same wave. Then this wave is possessing a temporal coherence, and for an ordinary light. It is due to spontaneous emission for ordinary light. This is due to spontaneous emission. There will not be maintaining any temporal coherence. But there will not be no temporal coherence. But coming to a laser, this laser is due to stimulated emission. This stimulated emission creates a continuous emission. As a result, the waves will be overlapping with each other. So this is the emission for the first transition, and this is another emission for the second transition, and this is the third emission, or this is for the fourth atom or the fifth atom, like this. And as they are maintaining the coherence, they will be overlapping with each other, and they maintain a temporal coherence. So the ordinary light cannot maintain temporal coherence because this is due to spontaneous emission, and due to the spontaneous emissions there will be random emissions where there will not be a chance of temporal coherence. But coming to the laser light, this is due to stimulated emission. The stimulated emission leads to the emission of photons in phase. In the first part of my lecture, I had revealed that the stimulated emission leads to the emission where the photons will be in the phase. If you recall the diagram what I had drawn, so these are the photons which will be in phase, and these photons will be emitting continuously, and this leads to the continuous wave, and this is called as a coherence length of the wave. Okay, so this is about the temporal coherence. And coming to the spatial coherence is the same definition. It is possible it is possible to predict, yes, the same definition, predict the correlation. I can write the same sentences, correlation of phase and amplitude at one point in the wave with respect to the phase and amplitude at another point other point. I'll write at other point in the other wave or in the another wave. So here I am writing it as the same wave, but it is another point in the another wave. So let me go for the diagram. So the spatial coherence, and now the spatial coherence will be like this. So for example, this is a wave, and say this is also another wave. If you look at there will be a phase at P1, and say this will be at a phase at P2, and now in this situation the 2 points P1 and P2 are in phase, and they obey a spatial coherence, and this is called as a spatial. There is a name itself, the coherence which is maintained in the space. even though the waves are little bit maintaining a space between them, hence the name spatial coherence. And this temporal coherence, where the word is a temporal, means a temporary, maintaining for a fraction of second and propagating throughout the medium. Right? So therefore, for lasers, for a laser, due to the stimulated emission, where the photons will be in the phase, and as the photons are in the phase, you see that all are maintaining the same phase. If you see, phase means if you look at the wavelength is the same, and the frequency is also same, that is the number of vibrations per second. Therefore 1, 2, 3, 4, let me go for an example, or 2 waves per second, 2 waves per second, frequency is same, and if you look at the wavelength is also same, and as they are maintaining the same wavelength and the same phase, this is said to be in a phase. And if they are also maintaining the same amplitude, and as they are maintaining the same phase and amplitude, the two parameters leads to the word called as a coherence. And fortunately, the laser will be maintaining both the temporal coherence and also the spatial coherence, which leads to the high coherent beam for a laser. So this is a main important characteristic of a laser. So let me review some of the important point. So coherence is nothing but the predictability of the phase and the amplitude at one point in a wave, or in the same wave, or in the neighboring wave also. And the coherence is of two types, that is temporal coherence and spatial coherence. Temporal coherence is the correlation of phase and amplitude at one point and with respect to the another point of the same wave. And this, for ordinary light there will not be temporal coherence, but for the laser it will be maintaining temporal coherence. And for the spatial coherence, it is the correlation of phase and amplitude of one wave with respect to another point in another wave. And as a result, for a laser, due to the stimulated emission, the photons will be in phase, and if they are maintaining a phase and amplitude, the two parameters leads to the coherence. And as the laser beam is satisfying both the temporal coherence and spatial coherence, the laser beam is a highly coherent beam. Right? So this is how you can make the notes by the key points. Now coming to the second parameter. So the second parameter is, if you recall, or if you review my video a little bit backside, then you can see the list of the characteristics what I had written. And the second parameter after the coherence is, the second parameter is a monochromaticity. So what is a monochromaticity? So the name itself, mono means single, chromatic or chromaticity is the wavelength. So here, if there is a radiation, and if radiation is said to be monochromatic, if I want to say that it is a monochromatic, so it possesses only a single wavelength, So in ordinary language, we can say that it will be maintaining a single color. Alright? So how this monochromaticity will be attaining, and what are the parameters? For example, if the energy levels are discrete, if the higher energy levels are discrete, that is very separated with a huge gap, then there will be a transition from higher level to lower level. There is a transition from higher energy level to a lower energy level. As a result, there will be a transition from E1, that is E2 to E1, and this transition is obtained as hnu, where hnu is equal to E2 minus E1, where nu is equal to E2 minus E1 by h. Okay, right. This is a frequency, how it will be depending. And now, if I say if I say that if the energy levels, if the higher energy levels are closely packed, if the higher energy levels are closely packed, then it gives to a number of transitions to the lower energy level. So it gives a number of transitions to reach to the lower energy levels, as there will be a, and I'll call this as a simply called as a spectral line width. Line width or spectral width. There are the two words called as a spectral width, or also called as a line width, which specifies the broadening. Which specifies the broadening of the frequency, which specifies the broadening of frequency denoted by a delta nu. So if there is a radiation in the interval nu comma delta nu, and automatically there will be a broadening to the, this is also called as a wavelength width. Automatically there will be a wavelength spreading of the spectral distribution leads to the monochromaticity. For example, the two, that is delta nu and delta lambda, are connected like this. Delta lambda is equal to minus c by nu square into delta nu, where if you look at for laser, delta lambda is almost 0.001 nanometer. If you see, the broadening of the wavelength is very less. The broadening is very less means it is maintaining monochromaticity, means it is maintaining almost, if you consider, if you apply the knowledge of mathematics, that is the delta lambda is the difference between two wavelengths. The difference between two wavelengths is very less, means it is almost merging into a single wavelength. As I am saying that it is a single wavelength, then this is the monochromatic. For ordinary light, so for a normal light, for ordinary light, so therefore this delta lambda will be high and in the order of 300 nanometers. So this, if the spectral broadening is very less, this leads to an important characteristic called as a monochromaticity. Therefore, for a laser, as the delta lambda, that is wavelength width, is very narrow, therefore the laser possesses a high monochromaticity. Let me recall some important points. So the radiation which is maintaining a monochromaticity is that is, it is possessing single wavelength, that is a color. And if let us consider if the higher energy levels are discrete, then the transaction will be from higher energy level to lower energy level, and the photon is nu is equal to E2 minus E1 by h nu. That is a single frequency. That is a single frequency. If the higher energy levels are closely spaced, then there will be a large number of transitions to the lower energy levels, which leads to the line broadening width, or the frequency broadening, or the wavelength broadening. The frequency broadening and the wavelength broadening is given by the relation delta lambda is equal to, and for a laser the delta lambda will be 0.01, very less, which leads to high monochromaticity. For ordinary light, so for ordinary light it will be almost 300 nanometers, which is not maintaining, that is almost, we can say it is a polychromatic, means multiple colors or multiple wavelengths. And coming to the third characteristic, is what we are saying. This coherence and directionality, this coherence and monochromaticity, and leads to, now you see, this leads to the third property called as a directionality. And then what is this directionality? There is a simple parameter that how the beam is collimated. Collimated means parallel to each other, means in the beam there will be a huge number of light rays, where every light ray is parallel to each other. That is collimated means the parallel, maintaining a parallel. How the beam is collimated and must travel to a longer distance. longer distance with a high velocity. So these parameters decides the directionality. The another word for the directionality is the degree of directionality is decided by important parameter called as a divergence. Then for the divergence diagram to be more clear, let we consider ordinary light. We'll consider ordinary light, and we'll also considering a laser light. So what is ordinary light? Let us consider a torch light, where the torch light light will be spreading, where diverging in all directions like this. So where the divergence is a very huge one. And coming to the laser light, so if I consider, so this is a laser light, and the laser beam will be almost monochromatic and diverging very less. So this is the diverging. And if I consider this at a point here, if A1 is the width or the diameter of the beam, and here if I consider this width is A2, and obviously A2 will be greater than A1, and if I consider this distance as D1 and this distance as D2, then the degree of divergence is given as so phi is equal to A2 minus A1 and by 2. Now I am considering the diameter into radius, therefore I have taken it as by 2, where it is giving a radius, and now so D2 minus D1. This phi must be very low. It must be very low. Very low value of phi leads to high directionality. If the value is very high, then automatically there will be a huge divergence. The divergence is also called as angular spreading. Angular spreading of beam in all possible directions. Okay, if you look at the diagram that the laser possesses, as the laser is traveling to huge distances with a high velocity, the spectral distribution or the distribution of the beam will be very low, where the difference will be almost very low. And when if you take the distances, automatically it will be very low. In the numerator, the value will be very low, and in the denominator the value will be more high, and as a result the total value, by the mathematical concept we can say that the total value phi will be very low, where the phi is known as high directionality, or it is also called as the value divergence. Therefore the laser possesses a high directionality, and then there may be a question, sir, how this directionality is achieved by the laser light? This directionality is achieved by the previous characteristics like called as a monochromacity, and also the first characteristic called as coherence. Monochromaticity and coherence. The coherence, that is maintaining the same phase and amplitude and maintaining the single frequency leads to the directionality, where the multiple wavelengths cannot propagate to the long direction, as you say, as in the case of ordinary light. But in the case of a laser light, as the light beams are in phase, as they are in a phase and maintaining so single frequency or single wavelength lambda, therefore this leads to high directionality, right? So let me go review. So directionality is how the beam is collimated and how longer distance it is traveling with a high velocity. The degree of directionality is decided by divergence, and this is the ordinary light. If you take a torch light, where the light wave will be spreading in all multiple directions, but coming to the case of a laser light, the beam is propagating in a sharp manner, in a unique direction, where the spreading of the light beam is where the spreading or the divergence of the beam is very low. If I randomly consider the spreading or the angular dispersion of the wave at point A1 or at a distance D1, the diameter is A1, and at distance D2 the diameter will be A2, then angular spreading or the divergence is given by a value, where if you apply the mathematics, the knowledge of mathematics, the numerator is very low, as this is in the order of nanometers, and if you take the distances here, it will be very high. As a result, if the denominator dominates, obviously the parameter will be decreasing, and at very low phi it is maintaining the divergence. And next, coming to the fourth point, in continuation to the fourth point, the fourth point is the last one. The fourth one is intensity or brightness. So this is a simple example where we will be looking in our daily life, where in our home we will be looking at a different source of light, like a 60 watt bulb and 100 watt bulb and a 200 watt bulb. So how this intensity is defined, how this intensity can be defined is, intensity is nothing but a brightness, and it is equal to the square of amplitude. Intensity is proportional to the square of the amplitude of the wave. So as I said that in a laser, for a laser, due to the stimulated emission, the photons will be in phase. Let us consider the first photon of amplitude A, and I also consider second photon of amplitude A. And as they are maintaining in the same phase, they superimpose constructively, or the superposition takes place constructively, or constructive interference lead to the constructive interference lead to the addition of the amplitude, and the amplitude becomes A plus A, that is 2A. And if I take that, becomes A is equal to 2A whole square, and then if you see the intensity, the photon 1 of amplitude A and photon 2, second photon of amplitude A, superimpose, as they are maintaining the same phase, they superimpose constructively, and that is called as constructive interference. And for a constructive interference, the total amplitude is equal to the sum of the amplitudes of the individual waves, and as a result, that is a 2A. Therefore, if I substitute in the intensity equation, I is equal to 2A whole square. Therefore, I is equal to 4A square. If you look at what happening here, when the amplitude is gradually getting added up or summed up, the intensity is increasing due to the square. And as a result, if we consider n number of photons, then the intensity equation becomes n square A square. So where A plus so on n photon, therefore I is equal to n square A square. So this leads to enormous intensity, that is enormous brightness. For example, let me give the comparative diagram for an ordinary light, intensity for an ordinary light, and also for a laser light. So for ordinary light, if I take a 100 watt bulb, then you can feel the intensity at a distance of 1 foot. At a distance of 1 foot, you can be able to view. This is our eye. You can be able to view with a distance of 1 foot without any disturbance or without any irritation or without any high intensity. With a distance of 1 foot, you can see the 100 watt bulb. But if you take the case of a laser light, and this is a laser light, and this laser light of 1 milliwatt, if you compare the value, so this is 100 watt bulb and this is only 1 milliwatt laser source, and you can feel comfortable with a distance of 1 meter, even though you cannot be able to view because the laser beam destroys or damages the retina of your eye. Okay, so this is due to high brightness. So this is how the clarification of the diagram for the intensity, where the intensity is very large for an ordinary light, and this ordinary light intensity is not maintaining. This is due to the spontaneous emission, where they will not be maintaining the coherence, and they will not be maintaining monochromacity, and there is a huge divergence. And for the laser light, this is maintaining coherence, monochromacity, and directionality. Therefore, the brightness is very large, and where you cannot view even with the 1 meter distance also, right? So these are the 4 parameters, and then there is a question, why the intensity? And I repeat the same process. This intensity is due to the coherence, and due to the coherence, these amplitudes are summing up. And as the amplitudes are summing, automatically intensity is increasing. And this coherence also leads to a directionality. So this coherence and the directionality make the amplitudes summing, and this amplitude summing increases the intensity, and this intensity is nothing but a square of the amplitude. And if you consider large number of photons which are in same phase, then the intensity increases enormously, which is proportional to the number of the photon square and also the square of the amplitude of the each photon. So this is about the 4th characteristic, that is called as intensity. So therefore, the intensity of the radiation or intensity of the beam is defined as the square of the amplitude, and for a laser light. So for a laser light, which depends upon the 2 letters called as a stimulated emission. And due to the stimulated emission, the photons will be in a phase. And if I consider the 2 photons which are of amplitude A and A summing up, and that overlapping of 2 waves is called as a superposition, or a superposition principle states that the the resultant amplitude is equal to the sum of individual amplitudes, and this is the principle of the constructive interference. And based upon the constructive interference, the intensity is squared up, and now we are getting the high intensity for a laser light, and the very low intensity for an ordinary light, and blankly we can say that intensity is the brightness. Okay, right. So these are the 4 characteristics. So let me give a review to the 4 characteristics in detail. So where you can make the overall characteristic at a view and at a glance, right? So the 4 characteristics are, so the first characteristics is a coherence. Okay. The second characteristic is a monochromacity. So I use the monochromaticity. That is the second characteristic. And coming to the third characteristic, is a directionality. Okay, and the fourth one is intensity, or in some textbooks it will be also written as a high intensity. Okay, right. The high intensity is a more apt word than an ordinary word writing intensity. So these 4 characteristics makes the laser highly efficient and highly energetic for different applications, right? And as I said, that the coherence is the prediction, or giving the correlation, of phase and amplitude at one point in the wave to the other point in the same wave. If I write a same wave, then this becomes a temporal coherent. And if I say that another wave, or a neighboring wave, or a neighboring wave, then this is called as a spatial coherence. And this coherence is of 2 types. The first type is a temporal coherence, and another type is a spatial coherence. So as I said, the temporal coherence is if we consider a wave, if I consider the 2 points, and these 2 points will be maintaining in the temporal coherence, and the laser light definitely obeys the condition of temporal coherence, because for ordinary light the photons will be in a random, that is due to the spontaneous emission, but for in a laser, due to the stimulated emission, the photons will be in a phase, And if I give you more diagram for you, clear diagram, you consider a photon which is like this, and another photon, so which is also in the same phase. Then this gives rise to, then the two combination of these gives rise to high intensity beam which is of the same phase. Okay, so the two may be superimposed because they are maintaining the same phase, and this gives rise to a continuous wave. And if I can, as this is a continuous wave, the length of the wave is said to be coherence length. And if I consider 2 points here, P1 and P2, obviously these 2 points will maintain temporal coherence. And coming to the spatial coherence, in the stimulated emission there will be large number of photons emitted, and these photons will be in if you look at so let me go for a clear diagram, because the phase representation must be very clear, otherwise the diagram and the concept will be mismapping. So this is maintaining the spatial coherence and spatial coherence. And if you see, so this is incoherence, and so this I will write it as a coherence. So this laser light will be maintaining a temporal coherence due to stimulated emission, and the spatial coherence is also maintained by the laser beam and due to stimulated emission. So as it is maintaining a temporal coherence and a spatial coherence, this laser beam is highly maintaining coherence, which is an important characteristic for the remaining which leads to the remaining characteristics. And coming to the monochromacity is nothing but a single wavelength. So where the spreading or the spectral width, or also called as a line width, is very narrow. The line width is very narrow for the laser light, and this if I consider this as the frequency width, and if I say that this is the wavelength width, then these two are related as a delta lambda is equal to minus c by mu square delta nu. It's a simple differentiation where you know that lambda is equal to c by nu. If I differentiate, delta lambda is equal to, so c 1 by nu is 1 by mu square, where that is for minus nu, and that is a delta nu. So this is if we differentiate, we will get this above equation where represented with a delta rather than a differentiation symbol d. So this delta nu for a laser will be very narrow and very low, in the order of 0.01 nanometer, which indicates that this is not of two spectral lines, but it is almost for a single spectral line. As I am saying that it is a single spectral line, this is of a single color, that is called as monochromaticity. Alright. So, and coming to the directionality, and for the directionality is defined as the quantity of divergence or the quantity of collimation to a larger distance. And I say that the ordinary light will be diverging in different directions due to the random photon distribution or due to the spontaneous emission. But for a laser light, it will not be diverged more, but at a certain longer distance it will be slightly diverging, the angular dispersion. And if I say that the quantity of dispersion at a point is width A1, and at another point if I take it as A2, and that distance is D1 and this distance as D2, then the quantity of divergence is given by A2 minus A1, which will be a very low quantity. I am taking that if I take it with respect to by 2, then it will be giving the radius, and this is D2 minus D1, where the quantity will be very low, that is the divergence is very low, means this divergence is very, very low, leads to high directionality. That is what we will say the important characteristic of feature. Then once again, if we repeat why this directionality, then I go for this is due to monochromaticity, and this is due to same phase. Here the laser beam emitted out is maintaining the phase and constant amplitude throughout its propagation. As a result, there will be a slight deviation as it is propagating through the medium for a longer distance, almost with a span of some 500 meters. Also, it can travel without a dispersion, without a slight dispersion. And this leads to the direction. And coming to the intensity is defined as I said, that is the square of the amplitude. And if I take a single wave, then it becomes a square. If I take two waves, then it becomes a two-way whole square. Why I am adding a two-way means, as I said, that the two waves will be in phase. When they are in phase, when these two waves are in phase, then the superposition and a principle comes into picture, and there will be an addition or summing of the amplitude. Then that intensity becomes a 4a square. And if I take n photons, then it becomes n square a square. Okay, and therefore the intensity will be very high. And for a laser, the intensity is more, and we cannot view 1 milliwatt, very negligible power for a laser. That is 1 milliwatt cannot be viewed with a naked eye, even for a distance of 1 meter also. So these are the important characteristic for a laser, that is a coherence, monochromacity, and directionality and intensity. If we go our lecture in a reverse manner, then automatically there will be a raising of the questions where, sir, why the intensity means phase? So why the directionality? Because of maintaining the phase. Why the monochromacity? So due to the lesser spectral broadening. And this is all due to, these are the three characteristics are due to an important characteristic called as coherence, which is maintaining all the emitted photons of a same phase and same amplitudes at different points of the wave, but not only in the different points of the wave, but also in the neighboring point, in the neighboring waves also it is maintaining the coherence. As a result, the laser is maintaining the temporal coherence and spatial coherence, and leading to the high coherent beam. This coherent leads to monochromacity, directionality and intensity, where I say that these all the characteristics are linked to one another. All the characters are linked to one another like a web. So therefore, as the characteristics are depending on one on the another, so these characteristics made the laser very highly energetic and very high efficient for different applications. Right. In the next session, we will be discussing an important concept regarding to the characteristics of the laser, that is population inversion, and the conditions for the laser, that is a 2-level laser system, 3-level laser system, and 4-level laser system. So you make the notes by looking at all the keywords and by the key equations.